Hello, Professor. We are group number 37 and we are working on continuous glucose monitoring project. So this is the pre-processing file where we take the MATLAB file that was given of the patient and then we convert it into a CSV file. This is the final data set that we get, and here's the bolus values, the date at which the bolus values were taken, the CGM values, and the date at which those CGM values were taken. This is the graph between the CGM and the bolus value that we got. So this shows all the points where the insulin was given to the patient, and then we remove the null NaN values from the data set and do some other processing like converting the decimal into the proper date time format, and then we got the final data set and we download the final data set. Then I have worked on the RNR LSTM algorithm to train the model for the prediction of the CG values, and finally whether the patient had taken meal or not. So I've taken epoch 100, which gave the best prediction. Then this is the initial importing of the data set, which has the time and the CGM values. Then I plotted a graph between the CGM values and the time, and saw the pattern that it was same throughout the data set. So then I divided the data set into train and the testing part, and over here I'm just scaling the data set and using exactly 60 previous values to predict the next value. Then here I'm training the model, so I'm using 0.2 as a dropout, and these are the neural network layers which are using the LSTM. Then finally I'm using 100 epochs to train my LSTM model, and this is where the model is being trained. So after completing the 100 epochs, I'm getting this as the loss of the prediction of the model. This is where I'm preparing the test data set for the prediction part. Then I'm doing the prediction over here. So these are all the predicted values that I got. So this is the mean square error, which is approximately 1600, and we can see that the calculated value and the correct value are very close enough, so that's a good prediction. So this is the graph between the correct CGM value and the predicted CGM value that we got, and this is the graph between the model accuracy between train and the test data set, the model loss between the train and the test data set, and finally the prediction table, which gives the recall F1 score. And this is the prediction where the true and the predicted value where the patient has taken the meal or not.
So coming to this ARIMA model, here we are importing a bunch of libraries, the main one being the ARIMA model. After that, we are loading the required data into a CSV file. So we are processing the data given in the MAT file, and we are taking the num CGM and date number values from it and pushing it into a CSV file. And as you can see here, there are some NaN values and infinite values in the num CGM array. So we are here we are removing those NaN and infinite values. Similarly, we are also loading the data from the patient2.mat file, which will be used as the test data. So we are also taking the num CGM value and date number here and pushing it into a test data.csv file. Here also we are removing the NaN and infinite values from the test data. After that, this is the predict function. So predict function is used inside the ARIMA model to predict the next CGM value. The get difference function is used to calculate the difference between two consecutive CGM values. This is the code for training the CGM data. So here we are using train data as the data which is given in the data2.mat file, and for testing we are using the patient2 data. The train data is stored in the past data, and this is then passed to the ARIMA function as a parameter here. After that, we are calculating the PR and MA coefficient here, and this spread is calculated based on the value returned by the predict function and the past data. So this is how we are able to figure out whether it was a meal or it wasn't a meal, and this is the output for it. We have also plotted a graph to visualize better. So here the green color represents the CGM values, and the red dot are the predicted meals. So as you can see here, most of the predicted values are at the peak of the CGM values. Also, to get a better representation of the data, we have also plotted the actual versus predicted graph, where blue is the actual CGM value, and it cannot be seen as it has been overlapped by the predicted values. Since there are around more than 8,000 values, it is difficult to interpret. So we have another graph of first 100 values from both the data. And here we can see that the model predicted quite well, except from the first part where the error is pretty high. Coming to the errors part, we have calculated the mean error per data value by calculating the difference between the actual and the predicted value. So here the mean error per data value comes out to be minus 0.023, which is quite negligible. And here is the graph for it. Along with that, we also have the mean absolute error and mean squared error, which is around 5 and 60 respectively.
Using the Kalman filter as an algorithm for prediction. So here we do the processing where we convert the mat file into a CSV file, as you can see on the screen, and right after that we have to make sure the date is in the right format, as in the original file it was in a decimal format. So we make sure we do that conversion using convert date, and our final conversions come in this format. And then the next step is synchronizing these CGM values and bolus values, because at some places CGM is nan, at some places bolus is nan. So those synchronizations are being done using the synchronize function, which is written at in a custom way. And the final result of the file is somewhat like this, which is then pushed into a CSV file over here, and these are the columns within it. So this processed Kalman final data.csv file is then used in the Kalman detection algorithm, where we import the file here, and we install filterpy, because that contains the Kalman library which we will use for implementing the Kalman algorithm. Now within the algorithm there are two functions that we need to define, which ultimately serve as the basis of how the Kalman algorithm will proceed. And these two are those functions which are then given as the input within the Kalman filter. There are a few other constants which also need to be initialized so that the weights can be initialized in a certain manner. And since Kalman algorithm basically trains itself on the go, and it does a prediction, updates its repository, and waits depending on how far it is from the original prediction. So that is why there is only one for loop which involves both training and testing. XS holds all the original values, ZS holds all the predicted values. Then ultimately error and accuracy are being calculated here, and then there is a plot between XS and ZS. Here you can see how extremely it differed in the beginning of the predictions, but ultimately the weights adjusted themselves, and then it is almost a perfect prediction with a 99.94% accuracy, and hence we do not see much of a difference between the two lines after a certain point. Thank you.
Hi, so this is a notebook for the random forest classifier model that we have used to do meal prediction from the CGM data. So initially I have imported all the libraries that I'll be requiring in this model. So first we have read the data d.csv. So this was the file which was created during the pre-processing stages. So I have imported this particular file which has all the data columns. So as we can see that the data has many null values. So to get better accuracy of our model, we need to remove these null values. So we drop the null values using drop NA. And now our data does not contain any more null values. So as we can see that the data consists of two parts, that is the bolus data and our CGM data. So I divided the data into two parts, two data frame basically, one containing the bolus data, that is act bolus delivered, as you can see, and the second one is the CGM data, which contains the date number and the num CGM values. So now as our data, as our main data, bolus data, for the bolus data our threshold value is 2.0. If our bolus value is greater than 2.0, it means that the person has taken a meal at that particular time. So we have converted the column at bolus delivered into a categorical variable containing meal or no meal. So whenever depending on the value of the bolus, whether it is greater than or lower than the threshold value. So since now this particular column is a categorical variable, to use it in our model we need to convert it into numerical value. So for that we will be using label encoder. So label encoder will convert our meal column into 01 categorical variable, in which 0 will stand for meal taken and 1 will stand for meal not taken. So I have created a new CGM database, that is CGM updated, which will have two columns, that will one will be meal and one will be num CGM. So after that we have initialized, we will be splitting our data into training and test. So in X I have taken the num CGM value, and in Y I have taken the meal value, and I have divided my data set into into training and test using the train test split method from sklearn library. So as you can see, the data is divided into train and test, and then we have used random forest classifier for the meal prediction from the CGM data. So I have trained my model here, and then I have predicted my model using the text values. As you can see, this is my train predicted. So I have printed the first 10 values of the train data and the predicted data, the test data and the predicted data. As you can see that they're matching, and the accuracy of the model is pretty good, which we did find out using the accuracy score method. So as you can see that our model is predicting 98% with accuracy. So I have also included a classification report in which we can see the number of labels, and we can see the accuracy and the weighted average, precision, recall, and F1 scores too for a particular model. Thank you.